Hello everyone, this is Dr. Hopkins with our next video in our series now where we're concluding with kinetics. And this is our second one on determining the rate law, and this time we're going to learn about the integrated rate law. And so this is kind of a slide I've used in the last two videos where the rate law, remember, is our concentration dependence of the reaction rate. It's empirically derived. The last video, we learned how to use the method of initial rates to determine the rate law. Today, we're going to learn the integrated rate law. So we're going to do a little calculus. So we'll start with a very basic, so it's just reactant A going to product. In order to evaluate the rate law using integrated rate law, we need to collect our concentration versus time data. Okay, so we'd have to go in the lab and collect a series of data or get a series of data given to us. Oops, sorry. So we would write, if this was first order, or any order, the rate law would be the rate of disappearance of A, so the derivative of A with respect to T. So this is calculus. Calculus is not required for the course, so if you don't like calculus or don't understand, don't worry, we're just going to get to an endpoint. And then if we had x equals 1, so it's first order, then that would be Ka. We would regroup our variables, so we would have our derivative on one side, our concentration on one side, and our time on the other. And then we can just integrate. Hence the name integrated rate law. So we would integrate dA over A from the initial concentration, or whatever we want to deem the initial concentration, to whatever concentration at time t. And we'd integrate K dt. The integral of dx over x, or dA over A, is the natural log. And so we would get the natural log of A minus the natural log of A at time 0 is equal to minus kt. Is the integral on the other side. And so we can rearrange that expression, that first order integrated rate law expression, into a linear equation. So y equals mx plus b, kind of the form of a line, where the natural log of a at any time t, that's a variable, equals minus k times t plus the natural log of our initial concentration. And if we were to plot, so we recorded all this data. If we were to plot the natural log of this data versus time, if it were linear, it means that it's close to a first order reaction, or x equals 1. And you'll notice in that equation that the slope is minus k. So we can do the same thing for x equals 0 and x equals 2. So both the 0th order case and the second order case. And if we do that, we get a table. I'm just basically going to show it. I'm not going to derive the 0th and second order. You can do that if you like. So here we have our order, the integrated rate law expression. So first order was natural log. Second order is 1 over the concentration versus time. First order is concentration versus time. And the slope always contains information about our rate constant. So once we've got this data, if we wanted to use the integrated rate law to determine our rate law, our rate law of a reaction, we just would plot our concentration versus time data for 0th, first, second, and second order, and then determine which one's the most linear plot, hence the r squared closest to 1. And then that's what we would call the order of the reaction in that reactant A. So an example, so we would plot maybe 0th order, so this is concentration versus time, and you can see it's not very linear, r squared is 0.88. We've plot first order, same data, natural log. Now we're getting a little closer, 0.97, that's not too bad, but still there looks like some deviation. And then we plot second order, and you can see the r squared is basically 1. So it's an exact match to second order. And our expression is y, so y would be 1 over concentration, x is time, and then the 0.2551 would be our rate constant. So once we have an integrated rate law, we have an equation that tells us how concentration changes over time. So we can determine, so if we wanted to know, hey, after 100 minutes, how much of reactant A is left, if we have an integrated rate law, we can do that. Or what's really important sometimes for some reactions is the half-life, how long it takes to to reduce a reactant concentration in half. So say if you started with 1 molar, at what point would you have half a molar left? And that abbreviation is T to the 1/2. I'm not going to solve the expressions for the half-life, but basically for first order, it's natural log of 2 over K, so it's independent of our initial concentration. So if we started with 1 or 0.5, our half-life is just a function of the rate constant, so it is not dependent on concentration. Second order, as you can imagine, or as we will eventually get to, it is dependent on the initial concentration. So T1, the half-life is equal to 1 over K A0. So if we've got this information, let's do a quick problem. If we have a second order reaction in A, we've got a rate constant that's 0.8, 1 over molar second. Now those units are second order rate constant units. Initial concentration of 0.16. Let's figure out the concentration of A after 22 seconds. So we're going to use the pen here. So our second order is equal to KT plus 1 over A0. So that's the second order rate integrated rate law. We have all the information. Let's just plug it in. So what we want to do is solve for 1 over A equals, now K is 0.80, and that's 1 over molar seconds. T is 22 seconds, plus 1 over 0.16 molar, because that's our initial concentration is 0.16. We plug that straight in. It doesn't go in as 0.16. It's 1 over 0.16 because it's the second order. And then we rearrange and solve. So rearrange and solve for A. And our A at time t, or 22 seconds, is 0.042 molar. So it's gone from an initial concentration of 0.16. 22 seconds later, it's about a quarter of that, so 0.042. So that would be our concentration. So you can see, using this kind of equation, we can know our concentration at any time t. We can predict when we're going to drop below some threshold concentration or so forth. And then the second part of this is the half-life. Well, if you remember for second order, and you probably don't, but we'll write it out. So it does depend on the initial concentration. For a second order reaction, half-life is 1 over K A0. So we would just plug in our K is 0.8, and our concentration is 0.16, and that's going to be, so this is, I should have used my units, 1 over molar seconds, and that's molar. So we're going to end up, it's going to be units of seconds, and we'll notice it's 7.8 seconds. So it takes 7.8 seconds for this reaction to reduce the concentration from 0.16 to 0.08. So then the concentration at that time would be 0.08, because that's the definition of the half-life. And we can use this information, first order, zeroth order, second order, doesn't really matter. Once we have the integrated rate law, we can use it to solve for concentrations, what are the concentrations at particular times, which can be very useful. And so these are the kind of takeaways from this from this video. Integrated rate laws involve plotting data, fitting it to the integrated rate law of zeroth, first, and second order, deciding which is the best fit, the best linear fit. And then once we have an integrated rate law, we can calculate concentration at any time. So it's actually quite a powerful equation we can use. And with that, we will continue next time.